Okay, so today I'm going to make a video of me working through this practice final exam. And actually, I've never seen these questions before. My coworker, Dr. Corrales, made this exam. And so I haven't, on purpose, looked at the answers. So I want you to get an authentic experience of what I do when I solve a problem. And then I also want to really encourage you on how to use this practice final. I personally have a lot of test anxiety, but even if you don't, this can be a really helpful thing to help you simulate what the exam is actually going to be like. Because a lot of times when we're studying, we can check back at the answers quickly, but you don't have that on the exam. So a very good test-taking strategy or exam strategy is to take a practice test. So I strongly recommend that a few days before your final, so that would be like Saturday morning for Dr. Corrales' students or Monday morning for my students, wake up at 8 a.m. when your final is going to be, or wake up a little earlier, go through your whole morning routine, have a nice filling breakfast. It's not going to make you have a sugar crash or whatever. And sit down in a quiet space in your room or wherever and take this exam all the way through. Don't stop and look at answers. Don't do anything like that. Just take the exam. And for those of you who aren't one of our students who don't have access to this file, you can just email me and I can share it with you. Okay, so here we go. This is how I would approach this question. Number one, which compound is a secondary amine? So for a secondary amine, they're going to have two carbon groups and one hydrogen attached to it. So I'm just going to look for that. A looks like a primary amine. It's NH2. This also is NH2. Two hydrogens attached. So not A, not B. Also on exams, it's really good to make sure the letter lines up with the structure. I've seen students get questions wrong just because the formatting of the key or the exam was just kind of off structure. C looks promising to me because it's NH2 with a CH3 off of it, or with CH3 off of it. So I think C is probably a right answer, but I like to check everything just in case. This has 3 carbons off of it, so this is a tertiary amine, and this has 2 hydrogens, 1 carbon, so this is a primary amine, so C is your right answer. A lot of times people get primary and secondary amines mixed up because you're looking at how many things are directly attached to the nitrogen, whereas with an alcohol, you're looking at the carbon that it's attached to, because there's only one attachment point for alcohol and halogens. You can't have multiple carbons bonded to the chlorine or the alcohol itself. So that's why we get primary, secondary, tertiary looking at the attachment point, but with amines, it's kind of different. So make sure you know the difference between those two. Which species is not a resonance form of the following? Okay, so let's look at this structure and go through our resonance rules. So resonance, usually we start at an area of high electron density. And even if there was a positive charge, we look at how we can fill in that positive charge. And we always want to make sure they're valid Lewis structures. So one of the big ones is we're not making too many bonds to an area of implied hydrogens. And those are kind of the 2 big ones that I can think of right now. So let's see. I'm going to draw this out so I can draw my arrows. So there's a carbocation here, which means there's 3 bonds attached to that carbon right there. So only 1 hydrogen. So if I move this lone pair over, or this the 2 electrons of this bond to fill in, I don't know why I said lone pair, to fill in and make a double bond right here, there's not too many bonds to this carbon because there's still 1 hydrogen there. And there's initially only 2 hydrogens on this spot to get 1, 2, 3, 4 bonds to carbon. So now the positive charge has moved over here. So I would say that's a valid Lewis structure. I'm also going to look at moving this other area of high electron density over. So that would fill in the positive charge there. There's only 1 hydrogen, so 1, 2, 3, 4. But we've lost our double bond here, so there's only 1 hydrogen at that spot on the ring, so now the positive charge has moved over. So I think that's another valid Lewis structure. There's not too many bonds to carbon or anything. And then the other thing I think we could do is move a lone pair over to fill in this double bond right here. So the positive charge moves, but now it's on the oxygen because oxygen starts with 6 electrons, minus 1, 2, 3, 4, 5. 3 bonds, 3 electrons would be plus 1. So all these are valid Lewis structures. Now, in the effort of saving time on an exam, if you're not very good at resonance structures, if you don't want to go through all of these, another option would be to just see if there's anyone that you find out that can stand out as suspicious. So like this first one, answer choice A. I'm looking at this and I see how the lone pair moved to fill in there, and this bond doesn't change, but how did the carbon get down, or the positive charge get down on this side? Like the thing that moved was up here. Nothing changed on this carbon down here. So why would there be a positive charge there? That doesn't make sense to me. So immediately this is suspicious, and it also doesn't line up with these other Lewis structures that I've already drawn. So that one's suspicious to me. B actually does look like the Lewis structure that I've already drawn, and it is easy to see how the double bond would come and fill in and leave a positive charge there. So that looks good. Looks like this one right here, the first Lewis structure I drew, the first resonance structure. And then the C looks like the carbocation we drew right there. And D looks like this last one we did. And E looks like this one in the middle that we did here. So A is the only one that we didn't find a structure of already, and it just has a positive charge kind of off in a weird spot. So that's kind of a way you can find the imposter. Oh, I guess I accidentally printed 2 of the first page. So that's the same one. Weird. Okay. I hope I have all the questions. I didn't even think to check that. Okay, 3. What is the major product for the following reaction? So this, quickly these reagents stand out to me, but if they don't stand out to you, then an option for you is to ask yourself, is this an acid-base question? Always go through, is it acid-base? That's some of the first things that we learned in chapter 3. And then is it a substitution or elimination? Or is it an addition that we learned to alkene or alkynes in chapter 8? If not, then is it something we learned in chapter 10, a radical reaction, or something we learned in chapter 11 by reacting alcohols and ethers? So that's kind of how I go through to check if it's any of those. This isn't an acid base, there's not an obvious acid or base. There's not a good leaving group, so I don't think it's a substitution or elimination, but there is an alkene, so I'm going to say this is probably something from chapter 8. That's kind of how I narrow it down. And I recognize these mercury, if mercury is ever present so far, what we've only seen mercury do is oxymercuration, demercuration, or alkoxymercuration, demercuration, and that's if it's in the presence of alcohol. This isn't in the presence of alcohol, so I think this is oxymercuration, demercuration, and oxymercuration, demercuration adds Markovnikov. It adds hydrogen on one side, alcohol to the other, so water across the double bond. It's one of the big three ways to attach water across the double bond that we already have talked about. So just knowing that, immediately I can get rid of this one. And then knowing that it adds Markovnikov, the hydrogen is going to go to the more substituted side. So it would go on, or the alcohol, would go to the more substituted side. So it would add like this. So we can get rid of the first one. It looks like actually the first one underwent rearrangement. So you would get that with H plus and H2O. This one is a diol formation. So osmium oxide and KMNO4 cold. This one is anti-Markovnikov. So you could get that with BH3, THF, H2O2, and NaOH. And then this one's also anti-Markovnikov. So again, you would get that. Well, actually, I guess this one you couldn't get with BH3 and THF because they need to add syn, the alcohol and the hydrogen. And in this case, they added anti. So this one you would actually get with BH3 and THF. So the only answer left is D. If you only know that oxymercuration, demercuration adds an alcohol and you know that it adds Markovnikov, just knowing that, you can get rid of of all the other answers. But I will say, oh, my battery's dying. Hang on just a second. Okay, hopefully that wasn't too much of an interruption. I will say that you should know that the alcohol adds on that side, the hydrogen adds on that side, and then you'll actually get a mixture of products. It's not syn or anti because it adds initially anti, but then when you do the hydration step to get rid of the mercury that adds initially, it kind of mixes up the stereochem. Okay, next question. Which would be the best method for converting 3,3-dimethyl? Okay, when I see something like this, I'm like, no, I can't do it. So immediately I draw 1, 2, 3, 4, 1, 2, 3, 4, 5, 1 pentene, so 1, 2, 3, and then 3,3-dimethyl into 3,3-dimethyl 2-pentanol. Okay, so actually this is a very similar question to the one we've seen before. This is not an acid-base reaction, and it's not a substitution or elimination because you don't have a good leaving group or a good nucleophile. So, and we see a double bond goes away and we add an alcohol, so that must be some kind of addition of water. And there's 3 big additions of water. You can get Markovnikov with rearrangement. That's from H plus and H2O. You can get Markovnikov without rearrangement. That's from oxymercuration, demercuration, which we saw in the first step. So HGOAC2 and water, and then there's an ABH4 and an AOH. And then you can get anti-Markovnikov. And so anti-Markovnikov, the alcohol would add to the less substituted side. Markovnikov, the alcohol adds to the more substituted side. So the alcohol added to the more substituted side. But if it had done that via a carbocation, there would have been rearrangement. And so our final product would have actually been this. And so I think the right answer to this question is oxymercuration, demercuration. And hopefully you can kind of use these questions to test your knowledge on the other things that come up here. Like, did you know all this stuff? If you did, what would be the product if you reacted that with those? That's kind of a way to further ask yourself questions when you're going through practice problems. Okay, which structure represents R and Z? Okay, well, Z is easier to find than R, in my opinion. And also, I like to make sure that these questions are that you all of them have methylheptene. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, well, that made life easier. If you can just count to 7, you can eliminate some of these. Although 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So only 2 of these are heptene, so I'm going to eliminate C and D based on that. And then Z is going to have them on the same side. Z, zame is how I remember that. E opposite is they're both vowels. So the major groups are going to be the one with the highest priority directly attached. So this side, you just look at one side at a time. It has a carbon over here and a hydrogen over here. Hydrogen is lower priority than carbon, so this is higher priority. And then if over here, hydrogen and a carbon, hydrogen is lower priority, it weighs less. So these are both 1 and they're both on the same side. So A is looking pretty good to me. And then let's see. I'm going to just do, we'll just do a big R chain over here. So this is your hydrogen. Okay, these are the same group, so they're equal priority. And then if you go here, it's a double bond, and this is another carbon. So the double bond counts as it being bonded to 2 carbons. So that is highest priority. So 1, 2, and then 3. So with the hydrogen pointing towards you, is that right? R, and then, so this should be S. So I think that there might have been a mistake in the answer key because this one looks right to me, where the methyl group is on the left side, and the larger ethyl group is on top. If you had this 1, 2, 3, that would be S, because the hydrogen's pointing towards you. You can flip it around and it's R, but this is only, and this is also Z, but it's only 6. So I think there might have been a mistake. I think this one was supposed to have a methyl here. So the right answer probably was supposed to be D with one more carbon off of it. Oh wait, no, that was my mistake. I didn't count the methyl on top. So this is the risk of you guys seeing me solve this in real time. I made the mistake of not counting this ethyl group. 1, 2, 3, 4, 5, 6, 7. So I did that question wrong. So D is the right answer because there are 7. So look, there's a mistake I could have made. So if something ever doesn't make sense to you like that, or I'm like, wait, this looks like it's Z, and but this is S, did I make a mistake? Always go back and check. And if you can prove to yourself that you did make a mistake in eliminating it, then change your answer. So this is 7. The highest priority groups are on the same side, so that's Z. And then we have a hydrogen pointing towards us, so whatever R or S we calculate, it'll be the opposite of that. This is the highest priority group, then this, and then this. And so it's S, but the hydrogen's pointing towards us, so actually it's R. So this is the only one that's R, Z, and heptene. But also just by knowing that it's Z, you could eliminate B and C, and by making sure you count to 7, but all these are 7, so I did it wrong. So that's what I get for trying to do shortcuts. So sorry if that was confusing for you. That's the risk of me having not worked through these practice problems before. But I wanted you to see how I authentically would try to solve this problem. Okay, so this next question, it looks like an addition reaction because there is an acid, but the only good base would be the alkene, and typically we've seen that as an addition reaction. So whenever I have H3O+, I rewrite it as H plus and H2O. That usually just makes the synthesis easier. And if you have an alkene and something positively charged, it will always attack on that positive charge first. And the hydrogen will add to this side and then give you a positive charge on the other side. And hopefully you recognize this as one of the big 3 ways to add water across a double bond. If we have an addition reaction, and it's H plus and H2O, that's usually going to be adding water across the double bond. There is a positive charge, so it can undergo rearrangement, but it'll do Markovnikov, and then this alcohol comes in and attacks. And so you have OH2 plus and your hydrogen on this side, and then it'll undergo deprotonation. I usually just write minus H plus because that's easier synthetically. Water or something else in the solution will come and take it away. And so you get alcohol added to this side. Now you might kind of be freaked out by the this like weird ring. That's one of the bicyclic rings we talked about very briefly. It's not important for you to know that for my class, but some professors would want you to know it. But if this type of structure comes up on an exam, just pay attention only to where the reaction is happening. The rest of it doesn't change, right? The only place that the reaction is actually happening is right there. And so the right answer should be D. Now, if you look here, there's a few things that you can kind of tell. This is anti-Markovnikov, so you need BH3THF to add that one. This looks like it underwent rearrangement, but it doesn't make sense for you to undergo rearrangement from one tertiary to another tertiary. That's not energetically favored, so it wouldn't happen. This is already tertiary. There's no reason for the carbocation to move over. This has the carbocation forming on a primary. That would not happen. And then this one just actually forces it to go through maybe another elimination, but that doesn't really make sense. So D is our only right answer. So I usually, when I'm taking an exam, not only do I try to find the right answer, but I eliminate all the wrong answers as well. So that's kind of how I make sure that I get my answers right. And you saw that helped me out whenever I made the mistake on that earlier question. Okay, which structure contains an oxygen with a formal charge of +1? Well, formal charge, you get the number of electrons from the column that it's in from the periodic table. So oxygen has 6. And then to get +1, you need -5 of something. And it's electrons from the periodic table minus bonds minus electrons bonded to it here. So some of my students say electrons minus dots minus lines. I don't feel great about you thinking of bonds in terms of dots and lines, but if that helps you get to the right answer, whatever works for you. So let's go through each of these. So this has an oxygen with 1, 2, 3, 4, 5, 6, 7 things around it. So that would be -1. This has an oxygen with 1, 2, 3, 4, 5, 6 things. 1, 2, 3, 4, 5, 6 things around it. So that would be neutral. Sorry, my pen, you have to really be kind of on top of it to write. This has 1, 2, 3, 4, 5, 6 things around it. So that's neutral. 1, 2, 3, 4, 5, 6 things around it. So it's neutral. This has 1, 2, 3, 4, 5 things around it. So 6 minus 3 bonds minus 2 electrons equals +1. So this at least has 1. But some of these answer choices have more than 1, so I'm going to go through all of them. This again has oxygen with 1, 2, 3, 4, 5 things around it. 6 minus 3 bonds minus 2 electrons equals +1. So this one also. See, this oxygen is 1, 2, 3, 4, 5, 6, so that's neutral. 1, 2, 3, 4, 5, 6, 7, so that's -1. 1, 2, 3, 4, 5, 6, 7, so that's -1. So the right answer would be 3 and 4, so that should be answer choice B. Okay, which molecule is achiral? So not chiral. So there's 2 ways that something is not chiral. Either there's no chiral centers, or there are chiral centers with a plane of symmetry. And that is a meso compound. These seem to have a chiral center. Both of these have 4 different things attached, which is what I look for a chiral center. 4 different things attached here and here. Here, this one's not. This doesn't have 4 different things attached. So all these seem to be have chiral centers except for this one. So it's not going to be the no chiral center, so we have to look for meso. Meso compounds, you need 2 chiral centers. There needs to be a plane of symmetry, which means they need to reflect one another. So basically the 2 chiral centers have to have the same 3 different things attached to it. And usually they're going to be R and S configuration. So one chiral center will be R and the other chiral center will be S. Okay. Well, I can automatically see right here on question 3, there's not 2 chiral centers, only 1. So that's not going to be our right answer because you need at least 2 chiral centers. It needs to be an even number of chiral centers. And then the next thing we look for is a plane of symmetry. And when I'm trying to find a plane of symmetry, I will line one atom up and see if the other atoms also line up. So both of these have 1 hydrogen, 1 bromine, 1 chlorine. All of these have 1 hydrogen, 1 bromine, 1 chlorine. So they both have a high possibility to be a meso compound. But let's see, these already have the hydrogen lined up and the chlorine and bromine aren't. So that's not a meso compound. So this is a chiral molecule. It has an enantiomer. And actually, I'll go ahead and calculate. This should be S, but the thing is pointing towards us, so it's R. And then 1, 2, 3. S, but the thing. So this is RR, so that it doesn't have 2 of the qualities that we need. Now, if we come over here, I'm going to choose just to line up the hydrogens pointing backwards. So we'll rotate this. So the hydrogen, chlorine, bromine. And then for the rotation, the hydrogen's down here. The chlorine moves over. And the bromine moves over. So there is a plane of symmetry right down the middle. The bromines reflect, the hydrogens reflect, and the chlorines reflect. So I think this is probably achiral. I think it's probably a meso compound. Let's quickly calculate the configuration. That's S, and the hydrogen's pointing backwards, so we can just leave it. And that's R. The hydrogen's pointing backwards, so we can leave it. So SR is another thing that we need for a meso compound. So 1 is definitely a meso compound, and it is not a chiral center. Or it is not a chiral molecule. It has 2 chiral centers, but it's not a chiral molecule. Okay, how many s-sp3 bonds are there in the following substance? Okay, so S means that it's not hybridized, means it only has an s orbital, so that's hydrogen. So how many bonds do we have where hydrogen is bonded to an sp3 hybridized carbon or something else? There's only carbon here, so carbon. So sp3 hybridized carbon have 1, 2, 3, 4 things bonded to it. It can be another hydrogen or another carbon. So let's look for all the places that there's an sp3 hybridized carbon. sp3, this is sp2. There's 1, 2, 3 sigma bonds. 1, 2, 3 sigma bonds. sp3, this should be sp2. 1, 2, 3 sigma bonds. This is sp3. This is sp3. This is sp2. 1, 2, 3 sigma bonds. Okay, so, and if you need a review on how to quickly calculate hybridization of different atoms, I actually have one of those on TikTok. I'll link it down into the description below. Okay, so 1, 2, 3 hydrogens. I'm just calculating the number of hydrogens at each one of these positions, so I can count how many sp3 hybridized bonds there are. I think that's all of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think 13 is the right answer here. Okay. Question 10, identify the hybridized orbitals involved in the C2C3 sigma bond. So again, to figure out the hybridization, I look at how many things it's attached to. So for carbon 2, it has 1, 2 sigma bonds, so it must be sp, a letter for each sigma bond. And then for 3, it has 1, 2, and an implied hydrogen because it needs 4 bonds total. So 1, 2, 3 sigma bonds, so sp2. So I believe this is an sp2. So the right answer would be, this is sp2, so that's not right. This is kind of tricky, sp2, sp, but it says in that order. Oh, normally it says like in the order of C2, C3. So I'm going to pick the one that's in the order of C2, C3. So that should be answer choice E. This has sp3, so that's not right. That has sp3, so that's not right. So E is the only one left. Oh, this is very tiny. I don't know if y'all can see that. It says Br2 and light, H nu means light, and then methoxide, methanol, and heat. Okay, so radical reactions, students actually usually do typically pretty well on them, but basically a radical is going to form at the most stable position. So 1, 2, 3, but it still needs to have a hydrogen abstracted, so there needs to be a hydrogen there. So I'm looking right here immediately. I see 1, 2, 3 bonds to carbon and a hydrogen. So with the bromination radical, the bromine would form right there and abstract that hydrogen, and then you'd get a bromine. So that would be the first step. And then the second, if you use OCH3 minus, methanol, and heat, then we have to ask ourselves what kind of reaction is that? I guess whenever I see light, I know that means radical reaction, but you do want to go through and make sure that it's a radical reaction. If you see Br2 and CCl4, for example, usually that's an addition to a double bond. In this case, we don't have a double bond. There's a totally unfunctionalized alkane as our starting material. So usually that plus bromine and light indicates to me this is a radical reaction. But you can go through each one and check just to be sure. And then for the next step, I'm going to ask myself, what kind of reaction is this? Well, here's a pretty good base, but there's no hydrogen, so it's not an acid base, no available acidic hydrogens. So not an acid-base reaction. And then the next question you can ask yourself is it a substitution or elimination? That's what we learn next in terms of reactions. And there is a good leaving group and there is a good nucleophile, so probably so. And when I'm doing substitution reactions, I look at substitution or eliminations to kind of tell which one of the 4 it is. I look at the nucleophile. This is a strong nucleophile, so that's going to tell me it's going to favor 2, either E2 or SN2. And then I say, are there any factors that would lend it to one or the other? Well, there's heat, and this is tertiary. So both of those make me think the next reaction will be an elimination reaction. Because there's symmetry, it doesn't really matter which one we take it from. Both of these have 2 hydrogens, so there will be one that's anti-periplanar. And I mean, it's symmetrical, so there's only one option. Usually for E2, you want to check for Hoffman versus Zaitsev. This is narrow, so it'll be Zaitsev, so the more stable. And then the next thing you want to check for is to make sure there's an anti-periplanar. Okay, so my initial thought is there's 3 hydrogens it could take from. It doesn't matter if it took from either of these two, it would be equivalent, or it could take from down here. To tell which one, these are less substituted, this is more substituted, so I'm going to say probably Zaitsev more substituted because it's a smaller nucleophile. And then for anti-periplanar, there's not any stereochemistry given, so I don't think we can tell in this type of question at the level that we're at right now if this one is anti-periplanar or not. So I'm going to say that's going to be your best bet. So your nucleophile would come in and take this hydrogen. The electrons from that would form a double bond, and your leaving group would leave. And I think this would be your answer. If this was a big, bulky nucleophile, I think we would go for 2 as the option, but since it's narrow, I'm going to go for 3. Okay, which of the following would be a reasonable synthesis of this thing? So let's see, 1, 2, 3, 1, 2, 3, 4 with an OH. So let's look at all the ways that it has a start. One is 1-butene. So butene is butane. I don't do too many bonds there. E and E indicates that it ends with a double bond. All these actually start with butene. Oh, you know what I just realized? All these start with butene, which is an alkene, so it's probably going to be an addition reaction. And here we have the 3 major ways to add water. This one adds Markovnikov with rearrangement. This one adds anti-Mark with no rearrangement. This adds this adds Markovnikov, with no rearrangement. And this one has methanol. So this is actually alkoxymercuration and makes an ether, not an alcohol. So it's going to be probably one of these. If we have an alkene and we want to add the alcohol on this side and the hydrogen on here, that alcohol is going to the less substituted side. So this is anti-Markovnikov, and there's only one way we can get that, and that's answer choice B. So that's how I would approach that question. This would give us the carbocation on the inside, and then the alcohol would add right there. This would give us the anti-Markovnikov, so the alcohol would also add on that side, and this would give us a methoxy group. So, okay, which of the following could not be a resonance structure of CH3NO2? Oh, here's a fun thing for you guys. I hate drawing NO2. I just hate it. It's not intuitive, and I always get confused. So nitrogen has 5 electrons, and oxygen has 6. 6 times 2 is 12. 13, 14, 15, 16, 17. So we have 1, 2, 3, 4, 5, and I think it's 6, 7, 8, 9, 10, 11, 12. Yeah, that should be right. And here's actually why I don't like drawing nitrogen NO2 nitro group resonance structures, is because this naturally has a positive and a negative charge initially, which I think is like so confusing and counterintuitive. But that means that one resonance structure started at an area of high electron density comes in here, but then that nitrogen would have an overly full octet, so another bond has to break, and an easy one to break is over here, so we get a very similar structure, where the negative charge on these 2 oxygens is actually shared pretty equally between these 2 oxygens. That is still positively charged, though, because nitrogen wants 3 bonds and a lone pair. And that is where another structure can come in that we can pretty easily tell. You know what I just realized? I don't even have to do this to myself. So this is how I would go through initially to make all the resonance structures, but resonance structures all need to be valid Lewis structures. And you're not moving any atoms. You don't move atoms when you're doing this, right? So you're only moving electrons. So I'm just going to do a quick check and see if any atoms are moved here. This first one looks like the initial structure I drew. This looks like the second structure I drew. This is a possibility that you could move the lone pairs back out, and you're only moving lone pairs to get there. But now there's two positives because this nitrogen started with 5, it has 3 bonds and no lone pairs, so it's +2. But it is still possible. It's least likely to contribute, but it is still possible. But then I noticed while I was drawing this over here, this hydrogen is supposed to have 3 bonds to it. That's how CH3NO2 starts out. So moving that over is not a resonance structure. It breaks one of the rules of resonance structures, and so answer D indicates to us that it could not be a resonance structure of CH3NO2. So I went to all this trouble to draw these, which always stressed me out for absolutely no reason. And that's a good reason that you can go through and eliminate wrong answers. It was helpful to make sure that these were all valid resonance structures, so because there was more than one of these choices as an answer, but we did check all of them are valid. We talked about why this one could work based on that. And so there you go. That's how it worked. Question 13. Okay. Question 14. What is the major product of the following reaction sequence? All right. Well, the first HI, this looks familiar. I think maybe we had this type of question on an exam. HI, the first thing that always happens, sorry, I started working this without talking about my thought process. If you have an alkene, it's usually going to be an addition reaction. It's not going to be substitution or elimination because there's no way to do a substitution or elimination on sp2 hybridized. We haven't talked about doing that at all, and there's no good leaving group. It's not an acid base because there's acid, but there's the only good base is an alkene, and if alkene is acting as the nucleophile, then it's going to be an addition reaction. So the first step is that alkene attacks, the hydrogen adds here, and the positive charge is here. The next thing that happens, if you have a positive charge, you always need to look for rearrangement. And in fact, this is a more stable, this is tertiary, this is secondary. So the hydrogen and the carbocation are going to do their little switcheroo, and you're going to get your rearrangement. You do still have this I- that was generated in the first step, and that will come in and attack. And you have this structure. Okay, now the next thing we have is tert butoxide and tert butyl alcohol and iodine. Okay, well, when I see tert butoxide, this tells me this is a good nucleophile. We have a good leaving group. This is a substitution or elimination. So then we look at the nucleophile. Is it strong or weak? If it's negative, it's strong. So tert butoxide is negative, so that's going to favor 2, SN2 or E2. There's a few factors that go E2 over SN2. SN2 is primary. E2 is if you have a tertiary leaving group, which you do. If you have a bulky nucleophile, which you do, or if you have heat. We don't have heat, but we have the other two things, so I think E2 is going to be the primary. When you have an E2 reaction, you need to make sure that you have Hofmann versus Zaitsev. And if you have the ability to check for anti-periplanar, you can do that as well, but because we don't have the stereochemistry and it'll be a mixture, just make sure that you're paying attention to Hofmann versus Zaitsev. So in this case, Hofmann is going to be a big bulky nucleophile. Zaitsev is the smaller, and it's going to give you the more stable substituted product. Well, we don't have Zaitsev. We have a big bulky one, so that's Hofmann. So it's going to give us the less substituted, less stable nucleophile. So that tells me it's going to take from here. So your tert butoxide is going to take from here. It's going to steal this proton to make a bond, and the electrons in the bond that were left behind will form a double bond, and your leaving group will leave. So I'm going to go all the way over here to draw my final product. Your double bond formed there, and you have this. Okay. So at first sight, it might not look like you have that, and you might be tempted to pick A because it's similar. But this is actually kind of tricksy. So A would be if there was no carbocation rearrangement to give your initial leaving group, and there was. So A is the wrong answer. B looks weird, but if you count, there's 5 carbons on the top, And we do have 5 carbons in our carbon chain here. So actually, I think B is the right answer because there's an alkene coming out of 3. It's just our answer kind of rearranged a little bit. C would be the right answer if after we got our iodine, there was a site F, so like an O- instead of a tert butoxide. And then D is, I don't even know how D would happen. You'd need to have 2 eliminations for the alkyne. We don't have that, so. Okay. Let's see. That's how I would solve that question to get to my right answer, answer choice B. Okay, question 15, pairs of enantiomers. So for question 15, I'm going to first look to see which one of these are chiral centers, because a lot of times on questions like this, they will trick you by not having chiral centers. So I want to make sure there are 4 different things attached. And there's 1, 2, 3. There's 2 CH3 groups, so that's not a chiral center. Here there's also 3 CH3 or 2 CH3 groups, so that's not a chiral center. This does have 4 different things attached to it. This does not have 4 different things attached to it. There's 2 hydrogens there. And this does have 4 different things attached to it. So right off the bat, the only possible answer is 3 and 4, which is C, or E, which is none of these structures. And so now we just have to compare 3 and 4 to see if those 2 are enantiomers. So this is a hard way that this, you would have to rotate this to tell. First, I'm going to say, are all 3 of these groups the same? There's 1 CH3, 1 hydrogen, 1 chlorine, and 1 propane group. So yes, these groups are the same. So now I'm just going to assign RNS configuration. If we're looking down at this one from the top, so that the hydrogen was pointing back, you'd have your CH2, CH2, CH3, CH3 here, and Cl here. This is obviously the highest priority. Both of these are carbons, so you have to look at what these carbons attach to. This carbon has an extra carbon attached to it. This has 3 hydrogens. So this is the next highest, and then this is the third. So this is rotating to the left at the top, so this is S configuration, and our hydrogen is pointing straight down, like right here. It would be pointing straight down at the middle. Now, on this one, if we look straight from the top, you'd get your hydrogen in it, so that's not super helpful. It would look like this if you look straight from the top. So I'm actually going to look from the side, and you'll have your Cl going up, your CH3 going up, and then your CH2, CH2, CH3 pointing down. That's how I solve this kind of question, because I'm not good at rotating molecules in my mind. I'm good at imagining myself standing next to the molecule for some reason. That's just easier for me. So if you view this one from the side, the priorities are still the same, and this is R. So one's S, one's R. These are indeed enantiomers, so the right answer is answer choice C. Okay, 16, give the IUPAC name. So first I'm going to count up my number of carbons. I find my parent chain. I number my substituents. And then I combine it all. So parent chain is going to start from the alkyne because it's higher priority than just an alkane. And it doesn't matter which one of these I go, they'll both give me 7. So it's heptane to start with. So I can immediately get rid of these hexes and the pence. Am I crazy? 1, 2, 3, 4, 5, 6, 7. The ones that have caused me the most problems here are just the plain old IUPAC numbering. So all of these are wrong. This is hex, 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 right? Hex, hex, pent, pent, hex. And there's 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so this is heptane. So I don't know what the deal with that is. It's containing the highest priority, so that should be right. So I'm just going to go ahead and give the IUPAC name for this. Sometimes the answer key is wrong, but since I was wrong on the last one, I don't want to just assume that. So it's 2-INE for the ine. And then 4 is ENE. And 6 has a methyl group on it. So I'm going to say, I would think this would be 6-methyl hept 2, or actually it'd be hept 4-ene 2-ine. So that is the name I would come up for this. Also, you can tell that these are wrong because none of them have the ene in there. So I think this might just be a mistake. I think this should be ene and then ine. I think the test bank probably made an answer here, but I'll make a note of that. Okay, the compound below is a hormone called cortisone. Which functional group is not present in cortisone? So I'm going to, before I look at the answer choices, this might trick you into looking like a carboxylic acid, but a carboxylic acid doesn't have the carbon in between. It's like CO and then immediately the OH. And so that's not a carboxylic acid. So I just want you guys to note that. It's an oxygen and a primary alcohol. And that's a ketone. This is a 1, 2, 3 tertiary alcohol. There's another ketone, and an alkene. So the functional group that's not present is carboxylic acid from this list because that looks like a carboxylic acid at first glance, but it's not. So pay close attention to that. Okay, question 18. What is the weakest intermolecular force? This is dispersion forces. Hopefully you remember there's dispersion forces, and then there's dipole-dipole. And dipole-dipole, if you have H with FON, a super strong dipole-dipole is called hydrogen bonding, and that's the strongest. We don't really talk about ion dipole at all in this class, so you don't need to worry about that. And covalent bonding is an actual bond, not an intermolecular force. So the right answer is dispersion forces, and the strongest would be hydrogen bonding. Okay, which of these represents R2-butanol? So I'm going to make sure that all of these are butanol first before I go and calculate all the R's. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All those look like 2-butanol, so that's good to go. So I'm going to assign the priorities. So alcohol is the highest, and then both of these are carbons, but if you look at the next one, this carbon has a carbon bonded to it, and this carbon only has hydrogen. So 1, 2, 3. So this is right at the top, so that seems like it could be R. Okay, for this one, I'm going to do 1, 2, 3. Actually, for this one, I'm going to draw it from the side. That's easier for me to visualize. So if I'm looking at it from this side, the CH3 would be on my right, the OH would be on my left. Oh, sorry, that is a reminder that I need to go to a meeting. The alcohol would be on my left, the CH3 would be on my right, and the CH2, CH3 would be pointing down if I'm looking at it from this side, right here. So 1, 2, 3. So that is S configuration. It's hard for me to rotate when they have the tetrahedral this shape for some reason, so I just try to arrange myself around the molecule in a way that makes sense for me. So if I look at this one from the front, the alcohol would be on this side, CH3, and then CH2, CH3. So 1, 2, 3. So this one's also S. This one, I would have to look at it from the left side. So the CH3 would be on the right, the OH would be on the left, the OH would be on the right. CH2, CH3. So this would be 1, 2, 3. So this one does look like it could be R. And then again, OH, CH2, CH3, CH, 1, 2, 3, R. So by my calculation, 1, 4, and 5, and it looks like that is answer choice C.